to present my work on powders. First of all, I will say that I am not an expert in generalized continua, nor in any continua. So I came here just to show you a very complex media and to see if you could be interested in understanding what is going on. So this work has been made in collaboration with the industry, several industries, and I will try to show you the qualitative important things in powders. Let me see. So I will discuss mainly the force between particles and how these forces, interparticle forces, affect in an essential way powder behavior. Then I will also discuss the hydrodynamic forces, because also these forces affect in an essential way the behavior of these powders. So what is a powder? It's easy. It's a set of particles in contact with gas and or liquid. And there is an example that everybody knows. So dry sand is air, solid air, humid sand is solid air, water, and saturated sand, solid water. This is, as we see, everybody understands, this is non-cohesive, this is cohesive and complicated, and this is non-cohesive again. So, well, why it is so difficult to model granular material and why really there are no good predictive models? It is because contacts are not like in solids. They are easily destroyed under the typical loads that are used in the powder processes. So also contacts are per nature non-linear, are viscoelastoplastic, so they have all complications and react differently to tension and compression. In addition, grains may rotate, deform, aggregate, and be destroyed. So, in addition, the initial state of the powder is important. Well, I would like to discuss the forces, the important forces in powders. So, there are gravity force, if we are on Earth, and there are attractive forces that are universal in the sense that whatever no matter what you do, these are there, these forces. And these are van der Waals of universal character, capillary forces due to humidity, they are easily present, and electrostatic forces due to tribocharging that are always present also. Also, because of the ambient fluid, there are hydrodynamic drag acting upon the particles. So the relation between these forces define practically determine the behavior of these powders. So one of these non-dimensional numbers is the bond cohesive number, which is the attractive force compared to the weight. And the other one is the drag force compared to the weight. Well, we define the boundary between cohesive and non-cohesive powders by this number. Bond number equal 1. Let us describe briefly the three forces that are present universally. One force is van der Waals forces. Van der Waals forces have this expression where R1, R2 are the local radius of curvature of the particles in contact. A is the Hamaker constant, and zeta known is the distance of smallest approach. When you compare this force to the weight, then if you consider a simple case, perfect smooth spheres, you see that for spheres below, these are special spheres, these are polymer spheres of density order 1 and Hamaker constant 0.5 10 minus 19 joules meter. So for these polymer particles, if you go below 2 millimeters, then these particles begin to be cohesive. If the particles are irregular, which is the normal thing, there are no perfectly smooth spherical particles in nature, then you go down to 75 microns if you treat, as we have done, with toner particles. These particles are used in serography. So this is important because these cohesive particles are usually small in size. We will see why in a moment. The other important force is due to humidity, water condensate on the at the contact points. As you see here in the photo, these are the liquid bridge, and then minimizing the surface tension of this for a given volume of liquid, you obtain the force that attracts both particles, which is given by this expression, and in contact with Z equals 0 is a maximum. Here shows what happens when you have a very small amount of liquid. When you have a very small amount of liquid, this R is the local radius of curvature of the asperities. Then, when you have enough, R is the radius of the particle. And another force that is always present is triboelectrical forces. This is naturally due to collisions, friction of particles. And this force is limited by electrical breakdown of the air. So in that case, if we use this upper limit for the charging by triboelectricity, we have the expression for the force. We can compare the importance of these forces for fine particles. You see that here, this is the distance, this is in microns. This scale is in microns, and this is in nanonewton, in newtons. Then, you see that van der Waals forces dominate, first of all, capillary forces, if present, they always dominate. Then, if the ambient is dry and capillary forces can be neglected, or the particles are hydrophobic, so it's not easy to form liquid bridge, the next force important for fine powders is van der Waals force. Then it comes triboelectricity. Triboelectricity equals van der Waals forces around 9 microns, and this has been the cause of a lot of controversy, because some people in the serographic industry, in the printing industry, say the fundamental forces are van der Waals. The others say the fundamental forces are tribocharger, and they never were in agreement. But you see why? No? Because this is really. Now, these forces affect in an essential way the behavior of this powder, and it's quite different to have non-cohesive powder as compared to cohesive powder in all powder processes. So I put some examples to show this. First, inertial regime is the typical regime when you put coffee or cereals in your cup, and in this regime, which is the regime typical of non-cohesive powders, the spacing is small and the stresses are due to collisions. On the contrary, the plastic regime is quite different. The velocities are quite small and the stresses are independent of velocity. You see here one case of this doesn't work. I have to imagine. Let me see. Stop. I don't know what's happening. Well, inertial regime, this is. A ver, ¿por qué? ¿Qué es lo que pasa con el tab? Déjame entonces. Inertial, déjame. Bueno, no, esto es de silo, ¿dónde está el silo? Ahí, no, no. Discharge this one. Okay. So you see this is smooth, easy, goes very well, no? Now, when you come to the plastic, no. Bueno, doesn't matter. I don't know why it doesn't presentación. Don't understand what happens. It's okay. Now we are going to examine another problem. This is the problem of plastic flow of cohesive powder. This powder that is here, this is a powder of around 100 microns of ferrite covered with a plastic film, and on top of that there is toner particles. And why the plastic, the film is to tribocharge the particles, and on top of these particles, the small particles, there are another nanoparticles that are called flow additives to control adhesion. So these toners, when they are deposited in the photoreceptor, has to be cleaned, and they are cleaned with a blade that press the photoreceptor and take out the powder. So now we are going to see, this is the wedge, between the plate, you see a wedge between the blade and the photoreceptor. The powder is accumulating here and going outward. So we are looking in this direction, and what we see is this. I'll tap, no? You see this. No, sorry. And blade cleaning plastic flow. This is the kind of flow that you have to expect from fine powders, from cohesive powders. So you see, it is not easy to model, but it can be done. Esto me va a llevar más tiempo de lo que yo quería, ¿no? Presentation. Okay, so now if we have one of these granular solids, they break usually under external loads. Here we are going to consider the breaking of powder layers, vertical powder layers, because it is much easier to analyze that three-dimensional body. So in this case we have this device, and we rotate the device. There is a camera on top of the device that make vision, no, a lateral camera in this case, that show you how the profile evolve in time. So I am going to show you the behavior of these two. Oye, ¿me puedes ver el tiempo? No, yo lo pongo. Pregúntale cuánto tiempo me falta, ¿vale? A ver, ¿cuánto tiempo me falta? Pregúntale. ¿Dónde está? 15 minutos. Cohesive, non-cohesive. Well, this is the case of non-cohesive. You see, it's going to break because these are under centrifugal forces. So you see how it breaks, has a characteristic profile. Now I show you the case of a cohesive powder, which is the same powder but with a different surface force, more cohesive, and you see that it breaks, but in blocks, in jumps, so it breaks discontinuously. So from this device you can estimate, doing a simple analysis, what are the cohesion of the powder and the angle of internal friction. Okay, so these profiles can be understood very easily. In the case, for example, of non-cohesive powders, is simply the equilibrium at the surface of a small element that says that when T, the tangential force, is equal mu times the normal force, then the powder, the surface flows. No, this is when we use this simple formula and we measure the profile, we see that it adjusts very well to the formula. In the case of cohesive powders, you see that the breaking is in blocks, in pieces. So you have to analyze this differently. You have to analyze, for the first avalanche, we use a method of wedge, which is very well known in solid mechanics, and for the outer avalanche, we use also a method of wedge. This avalanche, this wedge is going upward under the action of the centrifugal force, and we may, from this analysis, estimate how the cohesion varies, which is the important thing to engineers, and also, for example, how the angle of internal friction changes. It is interesting to note that the angle of internal friction does not change with cohesion. Well, now I come to hydrodynamic forces, to drag forces, and here again the situation is completely different for cohesive and non-cohesive powders. To understand what is this fluidized regime, I'm going to put a film, a short one. Here we have a fluidized bed. This is a suspension of powder particles. Here the air is flowing upward and the particles are suspended in the airflow. But the density is the spacing is of the same order as the interparticle ratio. So this is quite different from suspension, where the particles can be isolated in the fluid. This, for example, is this. This is only to show you what is a fluidized state. You see, it's like a liquid, but without surface tension. No? This is real. It is called fluidized state. Well. The fluidization of powders shows at least 4 different regimes that are very well known, and the regimes are shown here. These are for large particles, very large particles. These are for particles or the millimeters. This, when you go down, as you see here, is mean particle size, what you see here, and density. If you consider density for the one typical of polymer particles, you see that they decrease in size. As they decrease in size, the fluidization changes in character. So, for example, the largest particle fluidized in what is called D regime, which is this group D. All these regimes are used in the chemical industry, of course, because they are used to as reactive beds. So this is one type of regime that we are not interested, because this is for particles very large. Then it comes particles that are not so large, the type B, this is ordinary particles, and you see how when you flow air, it comes through the powder bed, and it is the expansion is very small. Okay. Then there is fine powder fluidization is type A. Where is type A? Sí, 5 minutos. Bueno, pues nada. 5 minutos only to show this. This is. So you see it's very homogeneous and expands enormously. This is the preferred situation for the chemist people. And then the others I will not show because they do not fluidize. They fluidize very badly. So, how we can understand this? Well, this is a point I have no time to discuss, though it is very important. But let us discuss the main one point that I wanted to show you is that the force, the minimum velocity you need to have fluidization has a known expression that is given there, and through sigma t, I mean, this is the viscosity of the fluid, this is the porosity, which is the 1 minus the solid fraction, this is density, part of the particle, gravity, size of the particles, this is the height of the bed, and this is the tensile stress of the bed, the force per unit area you need to break the powder. This is the velocity. We have measured this for our powders, and we obtain this expression. And here is for Stokes law, the velocity of suspension, and this is the typical velocity in the shear layer. And we assume that in the shear layer, the gas velocity is of similar order. When you plot then the velocity, these velocities in front of the particle diameter, you see the different lines. This is the suspension line, this is the fluidization line, this is the inertial line, and you see that for small particles of the order of 10 micron, when you increase the airflow through the powder bed, first you fluidize and then you suspend the particle. While typically, for sand or other particles, you first get the inertial regime, and then you get fluidization, and finally suspension. This is very important for the design of any apparatus in industry, because most of the works in granular matter is here, in the collisional regime. But you try to understand fine powders using the usual paper, the usual published papers, you are going to fail, because this regime is not even present. So this is very important. And I can show one example. This is the last one. Here we have made this experiment. We have put the powder here and rotate this and study the evolution of the profile. And you see what is here. Alta. And no, sorry, it was tambor. You see, this is what happens. When you begin to increase the velocity of the rotating drum, there are first a series of avalanches coming down and a slip of the powder along the surface of the rotating drum. But notice that the powder entrains air when it avalanches, and it takes a time to degas the wedge. When the time to degas the wedge is not big enough, then what happens is that the whole powder is fluidized in the rotating drum. This is a typical situation. So I am going to finish with the conclusion. The other case I don't want to discuss. Certainly, this media are very complex, no? And we have to take into account interparticle and gas interaction if we are going to deal with fine powders. Cohesive granular solids have very low density and are highly compressible. Well, initial flow we have seen that is absent, and the fluidization of cohesive powder is homogeneous and the expansion is very big. And for what I know, there are no continuum models for fine powders. Perhaps one here would be able to do some model or some research on this, and at least that was my motivation to come here and to show you these materials so that you can get an idea of how they behave, and perhaps you are interested in studying some of the regimes and making a model. Thank you very much.
Before we leave the room, there will be a short announcement by Paul. So first, can I use your computer?
Yes, of course.
In the meantime, we can have a discussion. Questions?
When your suspension breaks into blocks, the angle of the blocks seems to be the same. Are they somehow related to something?
The angle, you mean when in the rotating? No, the angle of this block changes all the time. But because the slope is steeper and steeper. So this change, and of course the analysis depends on the angle that we have initially, and we can study the evolution, but it depends on the initial angle.
Another question? Was there another question? If not, thank you very much.
Okay.